This problem is the stowage, loading, and placement problem for out-of-gauge cargo, meaning containers that exceed standard dimensions. The core decision is where each oversized unit should go on the vessel, so that loading is feasible and the ship remains safe and stable. Even though it looks like just placement, it is really a combined structural and handling problem. You have to respect slot limits, crane access, and lashing rules while minimizing operational friction. Picture the Port of Rotterdam heavy lift terminal handling out-of-gauge units such as flat racks, open-top containers, and platform containers. Each type can have different weight distribution, overheight clearance needs, and lashing patterns. The operational risk is that the wrong placement can compromise vessel stability, trigger hours of relashing and rework, or exceed crane and slot limits. Because this cargo is often high-value machinery, the cost of damage and delay can be catastrophic. Out-of-gauge cargo can exceed 66,000 pounds per container. That immediately changes what is feasible. Not every slot can carry that weight, and not every position has the clearance to accommodate overheight cargo. Placement must account for weight distribution across bays, height clearance, crane accessibility, and lashing patterns. The goal is not only to fit the cargo, but to fit it in a way that keeps operations safe and the vessel balanced. This deck is organized into 4 tiers. Tier 1 is an exact mathematical formulation. Tier 2 is a priority-based heuristic that scales to larger manifests. Tier 3 is a Sine Cosine algorithm, meta-heuristic that searches the solution space more globally. And Tier 4 uses few-shot learning to adapt quickly to new vessel configurations. Tier 1 models out-of-gauge placement as an assignment problem with multiple objectives. It chooses which container goes to which slot while respecting capacity and clearance limits. The formulation explicitly trades off total assignment cost, vessel stability contribution, and lashing complexity. That matters because a low-cost placement is not acceptable if it increases risk or makes securing the cargo too complex. The sets define the objects in the model, the set of out-of-gauge containers, the set of available vessel slots, and the set of container types such as flat rack, open top, and platform. Operationally, sets are about scope and traceability. You cannot optimize what you do not represent, so these sets define exactly which cargo and which slots are in the decision space. The decision variable is a binary assignment indicator. It is one when a specific container is assigned to a specific slot and 0 otherwise. Operationally, this variable is the plan itself. Once you have a valid assignment, the rest of the model's constraints make sure the plan is physically and operationally feasible. This slide introduces multiple objectives. One objective minimizes total assignment cost. Another objective maximizes vessel stability. Another objective minimizes lashing complexity. Operationally, think of these as 3 different performance lenses: cost and speed of execution, safety and balance of the vessel, and the practical effort to secure the cargo so it can survive the voyage. Total assignment cost captures operational effort and slot suitability. Stability contribution favors placements that keep the vessel balanced and avoid dangerous weight concentrations. Lashing complexity penalizes hard-to-secure placements, especially those far from crane positions where access is difficult. This objective structure keeps the model aligned with what causes real delays and safety risk. This constraint enforces that each out-of-gauge container must be assigned to exactly 1 slot. Operationally, it prevents the model from dropping a container to improve the objective. In reality, unassigned cargo means the vessel cannot sail with its plan manifest. This constraint enforces that each slot can be used by at most 1 out-of-gauge container. Operationally, it prevents collisions in stowage plans. If 2 containers were assigned to the same slot, the plan is not executable. This constraint ensures the weight of an assigned container does not exceed the slot's weight capacity. Operationally, it protects structural integrity. Exceeding capacity risks damage to the vessel structure and is a non-negotiable safety violation. This constraint ensures the container height fits within the slot's height clearance. Operationally, this addresses overheight cargo. If clearance is violated, the container may collide with other structures, interfere with cranes, or violate route restrictions. This constraint limits the total weight assigned within a bay, so the bay does not exceed its maximum safe weight. Operationally, this is about overall stability and stress distribution, not just individual slot limits. A plan can satisfy each slot but still overload a bay if too many heavy units are concentrated. This illustration provides context for slot structure and where out-of-gauge units can be placed. Use it to connect the model to the vessel. The math is not abstract. Each constraint is preventing a real failure mode such as overload, clearance conflict, or inaccessible placement. This example uses 3 out-of-gauge containers and 4 available slots. Container 1 is a 40-foot flat rack at 45 tons and 2.8 meters height. Container 2 is a 20-foot open top at 32 tons and 4.2 meters height. Container 3 is a 40-foot platform at 38 tons and 2.6 meters height. The reported optimal assignment is Container 1 to slot 4 with cost 90, Container 2 to slot 2 with cost 70, and Container 3 to slot 1 with cost 95. The total cost is 255 units. The key takeaway is that even small instances benefit from structured optimization. Tier 2 uses a priority queue to assign containers greedily. Instead of solving the full optimization exactly, it scores container to slot choices and picks high-priority assignments first. Operationally, this is how you scale. Large vessel manifests can make exact optimization slow, so a priority-based method produces feasible plans quickly while still considering stability and lashing factors. This slide introduces the priority function concept. The heuristic combines factors such as weight utilization, assignment cost, stability contribution, and lashing simplicity. Operationally, the priority score is your policy. If you overweight cost, you may harm stability. If you overweight stability, you may create hard-to-execute lashing patterns. The score weights control the trade-off. This slide shows the workflow. Compute scores, select the best assignment, update remaining capacities and constraints, then repeat. Operationally, the update step is where many heuristics fail. If you do not recompute feasibility after each assignment, you can paint yourself into a corner later in the plan. This is the first code segment for the heuristic. Operationally, focus on what is being computed, the priority score for each feasible container to slot pairing, and the data structures used to pick the best next move. This segment continues the implementation. Operationally, watch how constraints are checked before committing an assignment. A heuristic is only useful if it never produces an infeasible placement. This segment continues the implementation. Operationally, this is typically where the algorithm updates remaining capacity and tracks which slots are still available. This segment continues the implementation. Operationally, pay attention to how the algorithm updates vessel stability metrics or bay weight tracking as assignments are made. This segment completes the heuristic implementation sequence. Operationally, this is where output formatting and validation matter. Before using a plan, you want explicit confirmation that weight and clearance constraints were respected. The reported output assigns Container 1 to slot 4 with priority 0.82, Container 2 to slot 2 with priority 0.78, and Container 3 to slot 1 with priority 0.71. It reports total assignment cost of 255 units with 89% average capacity utilization. Treat this as a quality check. The heuristic is producing a solution consistent with the exact example. Tier 3 treats each assignment plan as a point in a search space. It updates candidate solutions using Sine and Cosine movements to balance exploration and exploitation. Operationally, this gives you a way to escape greedy choices. The algorithm can explore alternative assignments that may be slightly worse locally but better globally for stability and constraint satisfaction. This slide focuses on the Sine-based update mechanism. Operationally, the message is that the algorithm uses controlled random motion toward good solutions. It is a systematic way to search broadly early and refine later. This slide focuses on the cosine-based update mechanism. Operationally, it complements the Sine update so the search can move in different directions, improving the chance of finding a better configuration without getting stuck. This slide describes search behavior. Operationally, look for whether the algorithm is still exploring or has converged. If it converges too early, you may miss better stability distributions. This is the first code segment for the Sine-Cosine algorithm. Operationally, focus on how a candidate solution encodes assignments and how constraint violations are detected. This segment continues the implementation. Operationally, pay attention to how the fitness function combines operational cost, constraint violation penalties, and stability penalties. This segment continues the implementation. Operationally, this is where random parameters and step sizes are applied. The settings determine how aggressively the search explores. This segment continues the implementation. Operationally, look at how the best solution is tracked. In planning, you always want the best feasible solution found so far, not only the final iteration result. This segment continues the implementation. Operationally, focus on how infeasible candidate solutions are handled. Penalties must be strong enough to steer the search toward feasible assignments. This segment completes the implementation. Operationally, stop conditions and runtime limits matter. You may have only minutes to produce a stowage plan, so compute budget must be controlled. The slide reports that the Sine-Cosine algorithm converges to total cost 245.85 after 80 iterations. That is a 3.6% improvement over the heuristic solution. The improvement is attributed to better stability distribution and capacity utilization patterns, showing the value of global search. Tier 4 uses meta-learning, so a placement model can adapt quickly to a new vessel configuration using only a small support set of examples. Operationally, this is valuable because vessel layouts differ, and you may not have large historical datasets for every vessel type. Few-shot learning aims to adapt fast without retraining from scratch. This slide focuses on the support set. Operationally, the support set is the small set of examples used to adapt the model to the current vessel's slot structure and constraints. This slide introduces the meta-learning objective. Operationally, the objective is to learn how to learn. Build a model that can update quickly when it sees a few examples from a new vessel or a new cargo mix. This slide introduces the fast adaptation step. Operationally, this is the moment the model incorporates new vessel specifics. The goal is to shift recommendations towards safer, more feasible placements for the current configuration. This slide presents the few-shot learning workflow for out-of-gauge placement. Operationally, the workflow is take a base model, adapt it with a small number of support examples, then use it to recommend placements for the remaining out-of-gauge units. This is the first implementation segment. Operationally, focus on feature encoding. If weights, heights, slot capacities, and bay limits are not represented clearly, the model cannot learn the right constraints. This segment continues the implementation. Operationally, pay attention to how adaptation is performed. The update must be stable and must not overfit the few examples. This segment continues the implementation. Operationally, this is where the model is evaluated on a query set after adaptation. You want accuracy, but also feasibility. This segment continues the implementation. Operationally, monitor constraint violations. A model that is accurate in predicting past choices but violates weight or clearance constraints is not deployable. This segment completes the implementation. Operationally, output must be interpretable. The recommendation should be explainable in terms of capacity, clearance, stability, and lashing, not a black box choice. The slide reports that the model adapts to a new vessel configuration using only 2 support examples and achieves 94.2% placement accuracy. It reports that the adapted model recommends slot 4 for the 38-ton platform container with 63.3% utilization, while the baseline recommends slot 3 with 84.4% utilization. The practical meaning is that adaptation can shift the model toward more conservative, stability-conscious choices. This exercise asks you to formulate the model for 4 out-of-gauge containers with given weights and heights and 6 available slots. You must include objective, variables, and all constraints. Then you solve using the Hungarian method. If you can do this end-to-end, you understand the Tier 1 structure. This exercise asks you to implement a priority heuristic with weights for utilization, lashing, stability, and crane accessibility. You assign 5 flat racks to 7 slots and report the sequence and total priority score, which tests whether your heuristic logic is executable and consistent. This exercise asks you to design a sine-cosine algorithm with population 25 and 60 iterations. It specifies penalties of 500 for constraint violations and 100 for poor stability. The learning goal is to encode feasibility and stability into a single fitness framework.